Beth.
And I'm Beth.
Welcome to Physics with Beth and Beth. Hello. We are talking about apparent weight versus weight today. We're still in dynamics, that unit 2 in the AP Physics 1 curriculum. So let's just jump right in and talk about what apparent weight is versus weight. So weight, we know, we have a formula for an equation. It's mass times little g. 9.81 if you're on Earth, 1.625 if you're on the moon, and then wherever else. All right, but that is your weight. Now your mass never changes. If you were to go to the moon, your mass isn't changing, but little g is changing, which changes your force due to gravity, also known as weight. Okay, so what's apparent weight versus weight? Okay, so let's say you're on an amusement park ride. You're at the top, the very first hill, when you're at the maximum height, and you start going down it. You feel like you're coming out of your seat. You are coming out of your seat, but you feel lighter than you actually are. And then you go down and you hit the bottom of that big hill, and then you start going up the next hill, and it feels like there's a force pushing you into your seat. Okay, so you feel heavier than you actually are. That's apparent weight. So we're going to talk about that apparent weight feeling versus our actual weight of how much the Earth is pulling down on us, which is mass times our little g. All right, so we're going to start over here with a really quick problem that they like sometimes to put in this unit. And it's going to be about a pumpkin. It's fall, so I'm using a pumpkin as an example, but I have a pumpkin that weighs 40 newtons. When you see, this is your big clue right here, newtons. You have been given weight or force due to gravity, not mass. If it was kilograms, you would have mass. All right, so it's already been multiplied by g. In other words, this whole thing is equal to 40 newtons. It's a force. All right, so that's your clue on these problems. And then what they want to know is, what is its weight on the moon? If little g on the moon is 1.625. All right, here's the concept behind this. We know that if I did my force due to gravity, and this is on Earth, equals mass times my little g on Earth, that I would get that that's 40 newtons. I need my mass though, because my mass is going to be the thing that doesn't change. Mass is how much matter that makes up this pumpkin. So that's not changing whether it's on Earth or it's on the moon. The mass is still the same, but I'm going to need that to figure out my weight on the moon. My g, I know, is 9.81, and that's a scalar quantity. Remember, there's not a negative there. It's not about acceleration. Now, I'm going to divide both sides by 9.81 to get my mass. And I'm going to do that, and my mass is going to be 4.077 kilograms, because remember, all these laws are dealing with kilograms, so that's what it comes out in. Okay, now that I've got mass, I can definitely figure out what my force due to gravity, or also known as weight, is on the moon. I'm going to have mass times my little g on the moon. So that's going to be 4.077 times my little g, which is 1.625. You won't have to memorize. You'll either be solving for that, or they'll give it to you in a problem and you're solving for weight. Okay, and that's going to get my force due to gravity on the moon of 6.63 newtons. And I probably would have gone with two sig figs here, so that would have been 6.6 newtons. And that is your force due to gravity on the moon, or your weight on the moon of that pumpkin. That's how you do those. Now, let's talk about some more concepts in this unit. All right, so we have an elevator moving up, and we're just going to talk about some concepts first with scales, readings, normal, and then this elevator that we're talking about. They love elevator problems in this section. So elevator is moving up and slowing down. Okay, is tension in the cable less than, equal, or greater than the weight of the elevator? All right, here's the very first thing you have to do. We have to use that little concept I taught you in Unit 1 that I said would come back in every single unit. It's back now. That if you are slowing down, your velocity and your acceleration are opposite signs, or meaning opposite directions. Opposite signs, and the sign, of course, in physics just means direction. All right, so that's if you're slowing. If you are speeding up, your velocity and acceleration are same signs. So if you're speeding up, then velocity and acceleration are same signs, meaning same direction. Because again, signs just mean direction. And we talked about that in Unit 1. So first thing you do, I'm moving up. So velocity is always about what direction you're going. My velocity is positive because I'm assigning up as positive, down as negative. Elevator's moving up and slowing down. Slowing down, they need to be opposite signs. That means my acceleration is negative. Now I can start this concept problem. I'm not figuring out numbers. I'm going to go over here and do my free body diagram. All right, because every force problem starts with a free body diagram, except maybe this one, all right, that we just did. All right, I'm going to have tension in that string and that cable from the elevator, and I'm going to have the force due to gravity of that elevator. So this is my free body diagram. If I were to write that out and sum my forces in the y, I'm going to get that that's going to be mass times the acceleration in the y. I am going to have, and I probably did not give myself enough room, I'm going to write it over here bigger, that I have tension up, because I'm defining up as positive as always, and I have force due to gravity down, and that equals 0. Remember, force due to gravity is weight. They said, you tell me, I don't know why I put a 0 there, I'm so sorry, I got ahead of myself. Let's do acceleration first in the y. All right. Then what we're going to do is we're going to look at what this tension is, okay? So I'm going to solve for tension. All I'm going to do is add force due to gravity to both sides. All right, so I'm going to go over here, and I'm going to rewrite that up here, that my sum of my forces in the y equal mass times acceleration in the y. So I'm going to come over here, sorry, I'm out of room, and my tension is going to equal that force due to gravity, because I'm adding it to both sides, plus the mass times acceleration. Now you're often going to see this apparent weight as this formula. They're going to say weight apparent equals mg plus ma. All right, and that's exactly what we have here, is that our force due to gravity is mg plus ma. All right, now remember, this is the actual weight of the elevator. So here's the deal. I'm going to look at this formula now, and all these are really concepts. Once you understand, and when they're talking about tension here, in this specific one we're talking about tension, in a moment we'll talk about another force, but we have tension equals the force due to gravity, because I've added it over, plus ma. All I did was a free body diagram, sum my forces, tension was up, force due to gravity was down, and Newton's second law says it's equal to mass times acceleration. All right, now, we know that velocity is positive, so we figured out our sign on acceleration was negative. If I put a negative in here for acceleration now, so I have ma, but I now know it's negative because this thing is slowing down, I am taking whatever weight that this elevator is and I am subtracting something from it. I don't need numbers. I'm subtracting some number from my weight. So it's got to be less than. The tension in this example must be less than, because I have subtracted my mass times my acceleration. Okay, and that's all these problems are. They seem so scary. That's it. Now I'm going to go to moving up and speeding up. If I'm moving up, my velocity is positive. If I'm speeding up, then they have to be the same signs if you're speeding up. So my acceleration is positive, the same sign. So now when I go to my tension equals my force due to gravity, which is my weight, plus ma. Now I have my weight, we already know this stays the same, and I'm adding whatever number, I'm adding to that. So tension's gonna be greater than the actual weight of the elevator, because here's the actual weight of the elevator, and here, and put a little sign over that so it doesn't look like work, and I'm adding something to it. So tension is now greater. In this example, you're not going to know if it's less than or greater unless you figure out your sign on your acceleration. That is key. And you're only going to figure out the acceleration sign by figuring out your velocity and comparing them. Because look, here acceleration was negative and you were for sure slowing down. Here you're speeding up and it's positive. So you're like, oh, so if I'm slowing down, acceleration is always negative. No, no, no. We're going to do 2 more examples, so don't jump to that conclusion because that's not correct. It's about the relationship. Now I'm moving down. My velocity is negative, and I'm slowing down. If I'm slowing down, velocity and acceleration are opposite signs. So my acceleration is positive. Now I do that again, force due to gravity plus ma. Here's my weight, and my acceleration is positive. So I am indeed adding a number to my weight. Some number, whatever it is. I'm adding a positive number to my weight, and I'm going to get the tension is greater in this example. All right, now I'm moving down. Same thing. Velocity is negative because it's down. I'm speeding up, so same sign. If you're speeding up, same sign. So my acceleration is negative. All right, well, tension equals my force due to gravity plus ma. And now my tension, I have my weight here that stays the same. The weight of the elevator is not changing because we haven't changed it. The only way the weight of the elevator would change is if we took it to like the moon and had a different g. All right, so because it continues to have its same mass, the matter it's made up with. So our weight stays the same in all of these. And it's just about, did I add something to it or did I subtract something from it? I subtracted here, less than, added greater here. My acceleration is negative again. So I have a negative acceleration that I'm multiplying mass by. All right, so I've subtracted a number from my weight. I've subtracted some number here, and I'm now back to less than. So tension is less than the weight of the elevator because I've subtracted something from it. Now, what happens if this thing is moving at constant velocity or it's at rest? If it's at constant velocity or at rest, all of a sudden, and I'm going to come over here, my tension is now equal to my weight because there's no acceleration. So if I am going a constant velocity or at rest, acceleration equals 0. So I am left with just tension equal to our weight of our elevator, force due to gravity. Okay, this is going to work exactly the same. I am going to kind of erase some of this, but it's going to work exactly the same if they reword the problem and say, what is the scale rating? The scale reading. So in other words, they'll say an elevator is moving up and slowing down, but now what they're going to say, I'm just going to kind of erase this here and rewrite this so that you can see, because this is probably more common on how they say it. They say, will the scale, so an elevator's moving up and slowing down, a person with a weight of 100, let's say 700 newtons, is in the elevator on a scale, is standing on a scale. Standing on a scale in the elevator. Okay, so now what they're going to want to know, and I'm going to erase this slowing down and speeding up because we now know, and I'm going to erase this free body diagrammer and do it again. Standing on a scale in the elevator. I don't know why you would do this, but we just love having people stand on scales in elevators in physics. All right, standing on the scale in the elevator, I want to know if the elevator is moving up and slowing down, will the scale read more, equal, or less than her weight. Okay, and her weight's 700 newtons. All right, it's the exact same thing. It's just instead of tension, that scale is actually pushing up. It's a normal force. The normal force is the scale reading. All right, so instead of tension, though, you're talking about a person standing on a surface inside the elevator. Force down now, force due to gravity now is not about the elevator's weight, it's about the person's weight, which is mg. And we know in this example it's 700. It looks the same thing when you sum the forces. When you sum the forces, you're going to get in that y direction, you're going to get normal up plus a negative force due to gravity equals ma. All right, so I'm going to solve for normal again. I'm going to put it over here really big, that normal equals force due to gravity plus ma. All I did was add force due to gravity to both sides of this equation. All right, so now the normal is the scale reading. You go back and it turns out to be exactly the same, only instead of T's here, I'm doing N's. All right, if it's moving up, velocity's positive, speeding up, same signs. So I'm adding something to my 700 newtons, which is what her weight was. So it's greater, the scale is reading greater than her weight. All right, do it again down here, same thing. I am moving down and slowing down. So velocity is negative because I'm going down, slowing down, opposite signs if you're slowing down. So I'm adding, again, to that force due to gravity, her 700 newtons, I'm adding some number, so the scale's got to be reading greater. All right, then I go down to this one, and same exact thing, but instead of tension, it's normal, meaning what the scale is reading, because it's always reading what the ground's pushing up on you. All right, I'm just moving down, negative, I am speeding up, so acceleration is negative, so it's same signs, but I am now subtracting some number from that 700 newtons, so she's less than. So we have in this example, let me come back up to this example, we have that the weight is 700 newtons, you're moving up, so velocity is positive, acceleration is negative, you're slowing down, so you are subtracting a number from this weight of 700 newtons. So 700 minus some number is going to give you that the scale is reading less. Okay, what you do not want to do is assume that just because an object is slowing down, that your scale, like in this case it was slowing down, that your scale will read less than. Don't memorize that, because it's about this relationship between velocity and acceleration, and knowing if it's speeding up, same signs, slowing down, opposite signs, meaning direction. Because look, slowing down here, the scale's reading less than, but slowing down here, the scale's reading greater than. All right, so you really need to first figure out your sign on your acceleration by this relationship between velocity and acceleration, and then figure out in this weight apparent formula, if acceleration is negative, I'm subtracting from my actual weight, and weight apparent will be less. If acceleration is positive, I'm adding some number to my actual weight, my weight apparent is more. Now back to this scale again. If I have constant velocity or it's at rest, this elevator, then I have no acceleration and my apparent weight is exactly what my real weight is. All right, now that is your concepts. Now I'm going to show you very quickly, because I know these videos are getting longer as our material's getting more in depth here, that this is what a problem looks like with weight apparent. They'll say that we've got a 65 kilogram person that is on an amusement park ride and experiencing a force of 3 G's. Sorry, let's do 2 G's. Of 2 G's is what that'll say. Okay? And what they want to know is what is the apparent weight. So what is the apparent weight? That's what they're going to ask. Now we know what a real weight is. It's going to be 65 times 9.81 because this is on Earth. There's no amusement park rides anywhere else. All right. So we have apparent weight is what they want to know. All right. So here's what you're going to do. Your weight apparent, and that really just means if they're on a setting on a bench, like on a roller coaster, what weight apparent really is that force of the seat pushing up on you. Or if you're in the elevator, it's what the scale is reading, because it's reading the force of the ground pushing up on you. All right, so weight apparent is mg plus ma. All right, my mass is 65. I know that my little g is 9.81 on Earth. My mass again is 65. My acceleration is 2 g's. Okay, so in order to figure out what that is, 2 g's means you just take 2 times little g, which is 9.81. So that really looks like 65 times 2 times 9.81. And you're going to add that. That's what this actually means. Okay? You do that, and you're going to get a weight apparent of 1,913 newtons. All right, now that means that they are definitely feeling heavier than they actually are. Okay, that's it. Thank you for watching. I hope this helps. Way to hang in there, and happy physicsing.